We are all familiar with power delivery networks. The utility company transmits power from the power plant along high voltage lines. In your neighborhood, those high voltages are stepped down to a lower voltage that is used to power your house. And then you plug your phone charger into the wall to again step the voltage down to power your smartphone. Today we are going to see that power delivery networks in unmanned aerial vehicles can have similar distribution systems. Today's Tech Chat is brought to you from Mouser, and we are pleased to welcome Tom Curatolo, the Senior Director of Applications Engineering of Vicor, who will be introducing to us methods of building better UAVs through the use of modular power systems. Welcome to Tech Chat, Tom.
Thank you very much. Great to be here.
All right, so let's go ahead and get started.
Today, we're talking about how to create the optimal power delivery network using modular power components for applications in UAVs, unmanned aerial vehicles, also referred to as drones. If you are responsible for designing power systems for UAVs, you are probably asked to meet multiple requirements, such as maximum runtime and range, improve safety and reliability, add new functionality, increase or add payloads, change existing hardware, and then get it done fast. I'm going to go through some real-world examples in UAVs to show you how you can use a modular design approach to design a system that can be optimized for all these requirements. By using specific applications, this Tech Chat will show how creating a power delivery network, a PDN, at the beginning of the design process rather than at the end, and by taking advantage of implementing high-density power modules rather than discrete components to configure a power supply from the ground up, no pun intended, or a centralized power supply contained in a single box, which provides the optimal solution to meet your system's requirements. Also note that waiting to specify the power solution at the end of the design process can potentially risk creating a custom PDM that makes it difficult to reuse or upgrade as a platform or expand its capabilities quickly and easily. With some planning, swapping out a sensor or upgrading the payload capability won't force you to redesign the entire power delivery network.
No pun intended on the swapping as well, because size, weight, and power are obviously super critical for UAVs. And that power system, including the battery, but not limited to it, as you're going to talk to us about, really sets out limits on what the UAV can do, whether that's flying, sensing, data transmission, and how long it can perform those tasks.
That's a good point. Let's talk a little bit about what some of the possible solutions might be. Before we dive into the examples, I'd like to explain the concept of power delivery network. A power delivery network, or PDN, is more than just the power supply. It describes both the source of energy and all the loads, which in the case of UAVs is a collection of motors, sensors, high power processors, and other electrical subsystems, and also the strategy and implementation of how the power is distributed throughout the system. Take, for example, the UAV's batteries, which are an energy source, ranging from normally 12 volts to 400 volts or even higher. Typically, this source voltage is routed to directly power the propulsion motor drives, but there are other voltages needed within the UAV that are different. There may be other motors that operate at 12, 24, 48, or even 70 volts. Sensors at 5 and 15 and 24 volts, and processors at voltages of 1.8 volts or even lower, plus high-power GPU cards at 12 or 48 volts. Some PDNs are as simple as a single central power supply that houses all these voltages, which are then routed to each subsystem in the UAV. It's easy to implement, but not necessarily flexible and typically referred to as a silver box solution. While the selection of the silver box may be efficient in regards to your time invested, having to route those different voltages and currents, typically longer distances from that central location, can consume precious space and add weight, including the interconnect cables, which can make it susceptible to noise and external interference. Another option is to build the entire power supply yourself using discrete power components, but that requires considerable expertise, time, and effort. If you need to change something at the end of the design process, it can be disruptive and risky to your schedule and technical requirements. Fortunately, you can get the benefits without the drawbacks by designing a PDM that uses modular components.
Yeah, there's definitely not going to be a one size fits all solution when you need so many different voltages and so much different power characteristics, whether we're talking about the payloads or the motors, the data transmission. So, and I think UAV designers probably want to spend a lot more time thinking about the flight characteristics, the mission profiles, the types of those payloads, than they really want to about the power systems, right?
Yes, exactly. In the example of a tethered UAV where there's a long cable and it's connected to the airborne drone, considering the PDN at the beginning of the design process allows the system engineer to optimize the design of the tether and improve overall UAV performance, reduce cost, and minimize risk and potential supply chain delays. Considering future design improvements, such as increasing tether length for greater range, may come with considerations that increase drag even if it is thinner and may need more power to compensate. Fortunately, with modular power delivery network, it's easy to add additional power or capability as needed.
Yeah, the performance and the swap and the costs have always been a key for UAV designers, but the supply chain issues have been an afterthought until the last year, where, boy, that's really a big deal with our shortages of parts.
Exactly. A lot of folks are struggling with this.
That's right. So I think companies are going to be increasing their focus on the supply chain issues moving forward. So that's definitely going to be an important consideration as you talk about this stuff today. So give us some more information on those three solutions you outlined previously: the silver box, the discrete, and modular.
Absolutely. In the past, typical power supply solutions have been addressed with a power supply often referred to as a silver box, since it is typically components enclosed in an aluminum chassis with input and output connectors. This approach may be considered for its ease of use, but there are limitations that should be considered based on the requirements of the application that go beyond just the volts, amps, and watts. Often, the power requirements are addressed later in the design process, making it hard to define the final power requirements in regards to the electrical, mechanical, and thermal requirements. And often, the process of specifying and receiving a custom silver box brings with it a longer lead time than other approaches. Also, note that the silver box is typically easy to implement, but doesn't provide the advantage with modularity to change or expand quickly.
Yeah, big and heavy are obviously killers in these UAV markets, but really everything in the electronics world is getting smaller and smaller. So I would imagine these issues you're talking about have pretty broad application.
Absolutely. And in regards to getting smaller and smaller, there's another approach that we can discuss. And on the other hand, an approach with discrete components used to configure a power solution offers the system engineer the capability of a precise design for addressing the characteristic of each load. But the trade-off is better suited to a situation where there's plenty of time to address any challenges with the complexity and limited flexibility that would hamper meeting aggressive timelines. Plus, potential changes to the design would have a significant effect on your time to completion. The discrete solution is typically considered a hard approach in regards to a longer design and integration effort, plus risks due to supply chain issues. And while changes are possible, it will take additional time to repeat the work and revalidate the designs.
Yeah, so this is really then a full custom solution you're talking about here, correct?
True. In regards to the silver box, that's a complete custom solution. And then in regards to the discrete solution, where you're actually putting the parts yourself on the board, you're customizing it specifically to each load, which is sometimes a lot of work and takes considerable amount of time.
Yeah, so I would think that unless we're talking about the really high-end UAVs, the return on investment of doing that much design work for the power delivery network is really not going to be there.
Exactly. And we need to find something that's maybe in between, if you will. So that's where we look at perhaps modular solutions. So in regards to the advantages of the PDN, considerations in regards to efficiency, which relates directly to less losses and heat dissipation, plus weight, small size, and scalable power are significant attributes to the success of the power design. Here, the modular approach can provide a shortcut in design effort and minimize the bill of material, providing lower risk in the supply chain. It is worth noting that manufacturing these high power density modules on a panel is a low-cost, scalable process that is similar to semiconductors on a wafer. And we're showing the panel in the slide. A key advantage of the high-density modular approach in the UAV realm is that the less real estate and lower weight a power solution takes up, the more space available for the payload. So let's go over two real-world examples based on the work Vicor has done with leading innovative UAV manufacturers. The focus is on two specific applications, but the information here is useful across all UAV power systems.
That sounds great, Tom. So let's go ahead and talk about those two UAV applications.
Good. Now that you understand the value of a modular approach, I'd like to apply this methodology in our first example, a tethered UAV. Tethered UAVs are often used when a mission is needed close to the host vehicle or control base, where there is a need for long operating times, such as in hard-to-reach or dangerous environments, eye-in-the-sky surveillance, construction inspections, and over line-of-sight communications. Vicor has even provided a solution in a tethered UAV application for undersea surveillance and recovery, documented on our website. In order to control the UAV, a tether consisting of a number of cables bundled together is used to provide power for extremely long run times and for secure and reliable data transfer.
Yeah, we don't think about tethered UAVs very often, but anyone who's ever played with a UAV knows those flight times can be really short. I was just at a conference presentation recently. They were discussing some pretty complex and expensive UAVs, and their mission time was 15 minutes, I think, tops. And that's not enough for some missions.
Exactly. You have limitations based on the battery or whatever other power energy source you're using. So the tether really gives you a big advantage. Of course, there's a limitation to how far the UAV can travel, but still, for those applications I mentioned, there's a big advantage with using a tethered UAV. In this application, one of the biggest challenges is designing a lightweight tether that doesn't add to the UAV's weight and contribute excess drag while also being able to deliver power efficiently. These requirements are typically at odds with one another, as propulsion and electronic payloads work typically from voltages ranging from sub 1 volt to over 50 volts, making any length of tether very lossy. This leads the system engineer to consider higher voltages, maybe up to 1,000 volts as a source, and address the tether as a high voltage transmission line that then transforms and regulates back to the needed voltages on the vehicle. The figure shows that the basic trade-offs that are involved with this decision.
Yeah, and moving to higher voltages here for UAVs is really similar to the same reason that long-distance power transmission lines use really high voltages.
True. We're always fighting against distribution losses, if you will.
Yeah.
The advantage of using a higher voltage becomes clear in a tethered application. In this chart, we compare the power losses in watts of a tether using a 16-gauge cable versus the various lengths in meters that the tether length often needs to be in these types of applications. Obviously, it would be a major advantage to consider the use of an 800-volt source for a significantly lower loss of power versus the 400-volt source.
Yeah, even in your example here in the figure, a 16 AWG copper wire, at 400 meters, you're talking 10 pounds, 4.5 kilos. So you're holding up that tether instead of carrying payloads. So we need to make that as light as possible.
Exactly.
Yeah.
Very important decision to be made.
So in your earlier examples, you were showing step down from 48 volts. Is it reasonable to step down from 800 volts up on a UAV?
Yes, we've had a number of applications where there is a big advantage to getting it to higher voltages. We've even talked with customers wanting to go as high as 1,000 volts. So the challenge then is when you have this high voltage going up the tether, once you get on board, if you will, on the drone, you need to convert. So to accommodate the appropriate source voltage, whether it be 800 volts or 400 volts, we could simplify it with a product we call the bus converter module, which is a fixed ratio converter that transforms the provided source voltage to a working bus voltage. In this figure, we show a PDN where a bus converter module, BCM, is used to transform the 400-volt source to a 48-volt bus voltage on board to feed downstream DC to DC converters and directly power the drive for the thrusters.
So explain something for me. In the power converter world, does bus converter simply mean a voltage converter for fixed input and output voltages?
Well, it's a concept where we're developing an intermediate bus, if you will. So we have our source, which can be a variety of voltages, and it typically is not regulated. So you feed it into this bus converter, which basically, in the case of the BCM, to simplify it, it's like a DC transformer. So it basically takes whatever voltage comes in and divides it down by a certain ratio. So we have this specific example where we're taking a 400-volt source and transforming it down to 48 volts. Now that's not going to be tightly regulated, but the downstream converters will take that 48, which is more manageable, and regulate it for the loads.
Okay, that helps. Thank you.
Another application is a situation where the UAV design requires additional power for more payloads that add sensors, computers, LEDs, in addition to the thrusters. The host supply provided is 800 volts, and typically in this case it was plus or minus 5% regulation band. And it's sourced to a 1,000-foot tether to power 4,000 watts of peak power, plus payload and accessory power that divides down to individual onboard regulators handling 3,000 watts for the thrusters that need approximately 40 to 50 volts, 100 watts for the LEDs that require 2 amps at a constant current, a control/computing module that needs 12 volts plus or minus 5% regulation at 150 watts, and finally, cameras and sensors that need 15 volts with the capability of delivering 100 watts each.
So does that mean that some of these modules include the power conversion inside them so that if I'm swapping out my camera module, say that's running at 12 volts for a LiDAR sensor running at 6 volts, either one of them would connect directly to that 48 volt bus?
Well, it depends. If the 48 volts is sufficient for the load, sometimes you can get away with that. But oftentimes you'll need another stage of regulation, and it also convert to a specific voltage.
Okay.
So a cursory calculation shows a tether with reasonable ampacity above 7 amps will have less than a 30-volt drop at full power. So the first key modular component is this high voltage fixed ratio converter transforming the 800 volts to 48 volts and boasting greater than 97% efficiency, utilizing a near zero switching loss resonant tank power conversion topology, without the limitations of a regulation control loop, making for a low EMI but efficient conversion. The loads with the same ground can be powered by a non-isolated buck or buck boost converter without the need for isolation. The camera and sensors need a separate return, isolated from the others, so using a small, lightweight DCM type DC-to-DC converter is advantageous for this type of requirement. The PDN contributes to an overall lightweight approach for distributing the 48-volt bus across the vehicle to the location of each load to feed the localized onboard converters and provide the advantages of point-of-load conversion, greatly minimizing distribution losses.
Now, most of these advantages you've been explaining for tethered UAVs are also important for untethered UAVs, correct?
This is correct. It does transfer, absolutely. The untethered UAV application typically has more loads associated with its function, and therefore is often a consideration for how loads are distributed throughout the airframe and how a power delivery network is strategically implemented. The requirements of maneuverability and flight time are critical in making design decisions for powering the airframe. As an example, a solar-powered UAV may also use a variety of sensors to estimate wind speed and direction to assist with navigation and landing.
And energy harvesting here with solar is going to be a lot noisier and less reliable power supply than that 800 volt tethered supply you previously talked about. So is it a little more difficult to design the power converter?
It's a little bit more involved because there's more concerns in that regard, in regards to noise and EMI, and also, working against a limited time in regards to the energy source and things like that. So it's a little bit more complex than perhaps the tethered application was.
Right. That makes sense. And again, the efficiency then becomes so much more important because any wasted efficiency for an untethered UAV means you're carrying that extra battery up just to dump the power in the inefficiencies of the conversions.
Exactly. And let's go through an example here. Now, this is a lower voltage battery, but here's an example using a 24-volt battery in a 750-watt power delivery network for a delivery drone, which I think many folks have probably seen in some of the commercials that are running on TV recently.
Yes.
Unlike tethered UAVs, the typical delivery drone needs to be able to operate in complex, busy terrain, such as in urban areas. A delivery drone is an unmanned aerial vehicle used to transport packages, medical supplies, food, or other goods. These drones are typically autonomous. Delivery drones need powerful motors to keep both the drone and the payload aloft. Brushless DC motors are most typically used in drones because they have become cheap, lightweight, powerful, and small. Lithium-ion batteries are used in most drones because they offer enough energy and power, and they are relatively light, so they do not add excessive weight. In addition, the need for GPU power, logic, sensors, and long-range capability to be able to make it to multiple destinations and still have enough energy to return reliably to home base is the challenge with these designs. The 24-volt battery needs to support not only the motors that propel the drone, but also the many sensors in the drone, which are necessary for it to fly autonomously. Inertial sensors, such as an accelerometer, help the drone remain in flight by providing data to allow the autopilot to adjust motor speed in a multi-rotor configuration or control surface deflections with a fixed wing configuration to steer the drone. Navigation sensors, such as a GPS or magnetic sensors, aid the drone to fly along a specific path or to a specific destination by measuring the drone's location and orientation with respect to the Earth. Airflow sensors allow the drone to measure the airspeed, temperature, and density, and that information maintains safe control of the vehicle.
I think we've all seen in the power tool industry how they've migrated the batteries from 12 and then 24 and now 48 for better power, more efficiency, longer runtime. So it seems natural that UAVs are going to follow that same trajectory, correct?
That's a good example, exactly. And if your UAV needed more runtime between charges, the PDN needs to adapt. So upgrading, as you're mentioning, from a 24-volt battery to a 48-volt battery will increase the power density of the energy storage and extend your runtime. This presents two challenges to your UAV platform and the power delivery network that supports it. First is, how do you adapt your PDN to a 48-volt source and ensure the distribution is still appropriate in the same space without adding additional weight? Second is, how do you do this as quickly and with minimal disruption to the PDN? Fortunately, DCMs come in a variety of input voltage ranges, such that a 24-volt input part can be easily swapped with a 48-volt input part of the same size and power capability. In this specific case, it becomes a straightforward replacement to the original layout with minimal impact to the overall design used for the 24-volt battery system. Once again, designing your power delivery network up front and using a modular approach not only helps achieve greater performance, but also allows for quick and flexible scaling in anticipation of future changes.
So in looking at your graph here, what you're saying is that you can change the voltage on the left side of it, the input coming from the source, or you can change the voltage on the downstream depending upon your requirements for your subsystems, and the modular system can support any set of those kind of changes.
Yes, that's a great point. And that's one of the major advantages of a power distribution network approach with modular components.
And Vicor has a wide range of products to support UAVs and countless other applications.
Yes, and in summary, we encourage you to take advantage of these building blocks, often preferred for configuring a modular PDN solution. The isolated regulated DC to DC converter families of the DCM and the PI31 series, or the fixed ratio converters of the BCM family that provide a DC transformer function, and the non-isolated regulators of the PI37 buck boost and the ZVS buck families.
Okay, thanks, Tom. As we near the end of this tech chat, can you provide some final words of wisdom for our power system designers that are out here listening?
No, most certainly. While these are only two examples, they are relevant to other UAV designs. In fact, this modular methodology is useful across industrial, computing, and automotive applications as well. Whatever the application, Remember that you can create the optimal power solution for your system by using a PDN to create, distribute, and deliver power to your loads. Save time by easily selecting small, lightweight modular components optimized for their figures of merit, specifically efficiency, power density, and reliability, and provide greater flexibility now when you need it, with the added benefit of having the capability to reuse a PDN that can be easily expanded or scaled as needed in the future.
Well, thank you, Tom, for this great introduction to modular power delivery networks. It was good to have you on Tech Chat today.
My pleasure. Thank you very much.
And a special thank you to Vicor for lending Tom to us today and to Mouser for sponsoring today's Tech Chat.